And then we'll kind of learn some shortcuts for graphing. I don't think it'll be as painful as last semester. I won't make you use, I think, use 5 points to graph it. So we're a little more sophisticated this semester. We can shorten it up a bit, okay? So some definitions here first. Quadratic function. Here we go. You got to be ready to go here. We got lots of definitions. The first section. That's chapter 9. There's a lot. So quadratic function is a function with a degree of 2. Mr. Round. How was your weekend? It's good. I had to race my motorcycle, and that was fun. Let's go away. I was working. You went to work? I went to my mom's. Standard form. Here's standard form. We've seen these. This is called a quadratic trinomial. It's of the form y equals ax squared plus bx plus c. And we've been factoring stuff like what you see on the right here. The connection here is what we're going to do is use factoring to solve these quadratic functions in this chapter. That's what we had. That's one of the methods. We're actually going to learn 3 methods for solving quadratics because as I told you before, not all quadratics are factorable. Just all the ones we did last chapter. You know where we are. So, you know, when you launch something into the air and you model it with a quadratic equation or a parabola, that's the picture of the quadratic equation, you want to know where it's launched from and where it lands. So when you're factoring was a process that we use for finding where it's launched and where it lands, okay? How long it's in the air, that type of stuff. Parent function. This is the simplest quadratic. It's y equals x squared. If you know what y equals x squared looks like, you can use something you learned in 8th grade math. I think transformations. You guys do transformations of shapes. Remember sliding them up, down? Like that? I did 6th or 7th grade. Okay. Yeah. So when you did transformations, you can do that with a parabola. Okay. So it makes it really easy to graph it and know what it looks like in general if you understand transformations and the parent graph. Okay. Yeah. Parabola is the shape of a quadratic. The shape of a quadratic.
Are we going to start graphing these?
Yeah, we did graph these a little bit, but I'm going to show you how to some techniques for graphing them a little more. Not as many points that you have to plug in. Have a better understanding of the characteristics of a quadratic function. Really, in Algebra 1, we analyzed 2 functions primarily: the linear function, which was last semester, and the quadratic function this semester. So lines and parabolas are what we studied. And I'm going to give you some more details, I guess, than I did last semester about the parabola. Okay. Axis of symmetry. It's the line that cuts the parabola in half. It goes like this, right on through the middle. And it would be, if you creased this paper, or if you took your paper, creased it, and folded it over, the one half would fold right over the other. So, like, people are basically symmetric. There's all kinds of symmetry, right? You cut down the middle here, one half would basically mirror the other. It's not perfect. What's that?
That's how the body is like it goes like this.
Right. It is very symmetric. Yeah, it's very symmetric. So there's lots of things in life that are very symmetric. If you look out in nature, right? As you're going out in nature, and you look at flower petals, trees, leaves, very symmetric. They're symmetric everywhere. Bushes, yeah.
George.
So the vertex here, we've got a vertex on this thing. Here's the axis of symmetry. Let's see if I can get my axis. Maybe not. See if I can get my vertex to come on over. So the vertex, there it is. Can you see it in red there? It's the highest or lowest point on the parabola. In this case, it's the lowest point, right? It's the lowest point. So if you're modeling something with a parabola, that lowest point is called the vertex. Or if you're modeling a flight path of football going through there. By the way, in the pros, if a good punt, you know what the hang time is for a good punt?
2 minutes. 5 seconds.
5 seconds is probably about right, yeah. So it's in there about 5 seconds would be a pretty good punt, 50-yard punt, 50, 60-yard punt that's hanging in the air for a while. Give people time to get down there, to run down there. So, it reaches the highest point. If it's in the air for 5 seconds, it's going to take half that amount of time to reach its high point. So those are the types of things we're going to learn how to solve for, is finding the time it takes to reach its halfway point or its maximum, and the time that it takes to hit the ground. Yeah, and there, it's symmetric because of the symmetry there.
So I think God, it takes a shorter time. Huh?
No, it's the same because you have gravity working against you going up, and then gravity is working to bring it down on the other end. So.
Wait a minute, wait a minute.
No, it would be
Yeah, I guess
No.
until coming down.
No.
Well, because it leaves
Well,
at a
it's-
cer- it leaves at a certain speed and then comes back down.
Yeah,
Yeah.
it's nice.
So if I throw it to here, it is eventually going to be faster because it's going to get lower.
Yeah, listen
No,
to
it's not faster.
It would be.
Isn't
because
the lower
if
you
I throw
are,
it from right here, if it gets down to here, then it's going to be faster because I'll back it down here. So there's more power here, but then it's also going
It's
to
a- well, you're talking about the initial, the down force of the.
So
Yeah,
yeah, if I throw
but in
it,
terms of but in terms of symmetry, if you were to take,
if it starts
just-
here and ends here,
Okay.
it's going to be the same speed.
yes, that's it. If you take and continue the parabola back behind you, and then you continue it ahead, you will have a symmetric parabola with the same amount.
Shut up.
All right. If the value of A is positive, now A, going back over here, okay, A is this number in front of the squared term. We've looked at that a little bit so far. Okay, we've been factoring, because when A was 1, it was a simple quadratic. We could just factor it by using our big X, and once we had those side numbers, we had it. And if A was not 1, we had to then divide through by A. Now, we're looking at A again on this, but if the A value is positive, okay, the parabola faces up, and the vertex will be a minimum.
Okay, I'm gonna put it. For max, it's negative.
Yeah, if the value of A is negative, then the vertex, it'll face down, and the vertex will be a max. It's got to be either one or the other. So all the parabolas we study in this class are either facing upward or downward. When you move, you can, when you get into Algebra 2, you'll study parabolas that actually can go right or left. Yeah, but they're no longer functioning. So you would look at, I need one that's, let me find an equation.
Wait, which one?
You just look like right here, that's positive. If I put a negative sign in front of it, it would face down instead of up. And that's just helpful to know if you're going to quickly graph it. Can you guys locate the max here? What is the max? Can you tell me the coordinate of the max?
3.
Okay, it would be 0, 3, and that is a max. And we just label the coordinate of the max. Don't just say 3.
0, 3.
Okay, but we want to label it 0, 3. The max y value is 3, but if we give it a coordinate, it would be 0, 3. What about this one for the min?
0, 2.
It's 1,
What the?
negative 1. Yeah, 1 negative. So 1 to the right, 1 down is the minimum.
I'm going to be bad at this.
No, I think you'll be good at it.
Because I don't like graphs.
But I'm going to show you kind of, you'll know enough about the quadratic functions that it won't be hard to graph them. I'll show you. By the end, it'll be okay. So what about here? Minimum, and what is it?
Wait,
Yeah,
minimum.
negative, it's minimum, and it's negative 2, negative.
That's not upside down though.
No, you're this.
That's upside down?
Wait. No, it's negative 2, negative
No, we would consider this right side up, but if it's facing upward, then the vertex is a minimum.
Oh, but then it's facing
Downward.
max. Okay, I got you.
So the goal for this, at least in this lesson, we're going to be graphing quadratics that don't have a middle term. So we'll get in the next section into some that have a middle term. I'll show you how to calculate the vertex. But here we're going to graph the function y equals 2x squared. First of all, is it facing up or down?
Both.
Only one or the other. This one's going to face up.
Which one?
This is going to face up because 2 is positive. We'll list the domain and range. We had started last semester, I would have you plug in negative 2, negative 1, 0, 1, and 2. We really don't need to do that. If I make a table here of values, just make a table of values, if this is fairly similar to the parent graph, a good value to try in here is 0. Let's just place 0 kind of in the middle of our table. because I'm going to have you pick one value to the left of the vertex and one value to the right. And eventually we'll learn that if we can get the vertex and just one other point, like the y-intercept, because of the symmetry, that's enough to graph a parabola. So you can graph a parabola just 2 points if you know kind of what they look like generally. So if I have a 0 here, we need to pick at least one other point on each side. We could choose 1 and -1, although those are going to make it kind of close together. So we could choose -2 and 2. I think that's what I'll choose here. So here's what it looks like. We have y equals 2 times -2 squared. You have to understand, if you're plugging this into your calculator, guys, you've got to put that -2 in parentheses. I think we can do this without a calculator. -2 squared is positive 4. Plus 4. 4 times 2 is 8. And then if I plug in 0, 2 times 0 squared is going to give me what? 0. And then y equals 2 times 2 squared. Whether it's a negative or positive 2, I'm squaring it. So I get the same value. It will be 8 again. And you can see that it's very symmetric. If the vertex is at 0, 0, and I know one of the coordinates is 2, 8, the other one has to be -2, 8. So it's a parabola facing upwards. Sometimes when I draw these, I'll just do half of it at a time. But with just 3 points rather than 5, like we did before, I was making you plug in -2, -1, 0, 1, 2, right?
Yeah.
We can graph these. And like I said, as long as you know the vertex and then one other point, that'll be enough. All right, what about this one down here? We want to be smart about the values. Oh, before we do that, sorry. What's the domain here?
Domain?
I draw an arrow right here. See that arrow? What does that indicate? It keeps going up, and it's going to keep moving. It looks like it goes vertical, but it's going to keep moving to the left forever. Okay. This one right here is going to keep moving to the right forever. So if x can be anything all the way to negative infinity and anything all the way to positive infinity, we would say the domain is all real numbers. Okay, and that's going to be the case for all of our parabolas here that we're looking at. We're studying parabolas that are all functions. Functions are all, the domain will be all real numbers every time. The range, good question. The range will vary. Okay, the range is going to depend on the min or max. So there's the min. The range are all the possible y values that could be on the graph. What's the lowest y value that could be on the graph of this parabola?
0.
0, yeah. So y has to be greater than or equal to 0. Now it will always be a greater than or equal to because 0 is included in this.
Exactly.
So the range will change. The domain will always be all real numbers on all of the parabolas that we're studying. So as I go to this one and I make my table, let's be smart about the table. Would 0 be a good one to use again on this?
Yeah.
I think it will be. Because what's the vertex going to be here? Put 0 in. It'll be 0. The vertex is going to be 0. Which way is this one facing, up or down?
0.
It's facing up because A is positive. It's facing up. What would be a good value to choose to the left of 0 so that it comes out evenly?
Negative.
Yeah.
Negative.
-3 and then +3. So I've got y equals 1/3 -3 squared. And I'm going to get the same result when I plug in +3. So
Wait, why are we getting positive negative?
because of this 1/3 out in front, we think it would be smarter to do 3 or -3 rather than 1 or -1 or 2 or -2, right? Because 3 squared, -3 squared is 9. 1/3 of 9 is 3. And I'm going to get the same thing on the other end here when I plug in +3. And so I have -3, 3, and +3, 3. And you'll notice that this parabola is a little bit wider than the previous one.
Wait, I have a question, John. So basically, for the first one we did, we just used 2 instead of 2x squared.
We actually, no, it wouldn't have mattered in this one because it wasn't a fraction out in front. We could have chosen 1, we could have chosen 3, we just chose 2 because it was a little farther away from the 1. Like when I'm trying to graph this one, if I put in 1 here, 1 squared is 1, times 2 is 2, I'm at 1, 2, and my points are all really close together. And so it's a little better to graph it maybe with the points a little separated out. That's the only reason why we jumped to 2.
Whatever number you have, like, say you just put like a 2 in there, so then it'll go up in 2s. So
Yes, because of the 2 out in front here.
okay,
Yeah,
so
right.
if we chose like 4, it would go up in 4.
Well, if we chose 4, we're going to square it first, so it'd be 16, and then times 2 would be way up at 32, so it's going to go up by more.
With the x, so if we chose like 4 with x, would that be going up in 4s?
No, because we have, if we choose a 4 here, we're going to square that 4.
Yeah.
I know.
So it's going to go way up, because it's going to get squared. 16 times 2 is 32, so it'd be way up off the
That would be like 4, 0, 4, 8.
No.
I would only choose those if this were a 1/4 out in front. That's so I would look at the fraction out in front, and I would choose a number that's a multiple of the bottom of it. Okay. What's the domain? Yeah, all real numbers. So on your homework, when they ask, "What's the domain?" If you want to, you can use this little capital R. It's like a double, it's called a chalkboard script R here, but you can use a big R if you want. That'd be shorthand. I would understand that. For all real numbers, And then the range is going to be different. On this one, it's Y. How come I'm choosing Y for the range? Do you remember?
No.
Oh, because y
Now,
has to equal something.
Y has to equal something.
It does, and the Y-axis is the range. It's how far can the graph go up or down, or what are the possible Y values, but we got greater than or equal to 0. I haven't shown you any yet that weren't that same range. The range will vary. I'll show you in a little bit here. But that's it for the range. So we also mentioned another characteristic here besides which way it's facing and graphing it. There is a difference in terms of how wide or narrow the graph of the parabola is.
Oh, that's weird.
What's that?
That was weird.
So these are little screen captures of the graphing calculator. Okay, these are 3 different screen captures. So on the graphing calculator, when you get to use one,
Casio.
you get to add algebra 2. Yeah, you may choose that.
Casio.
Yeah, Casio. So
Casio.
as you graph these, you'll notice that certain ones are wider than others. Okay, certain parabolas are wider than others. Can you tell just by looking at this? Like each of these model the different functions here. Like what makes it wider, the parabola wider? What type of value for A would make it wider? A bigger number would be one possibility. Now, here the number is 1. Here the number is 1/4. Which one would you say is bigger? This middle one at 1, or wider, I should say, the 1/4 or the 1?
1/4.
So it looks like it's actually going kind of the other direction here.
So smaller than number.
Yeah, but here's the thing. This is the smallest number up here, right? The -4.
Right.
But it's the narrowest graph. So there must be something having to do with maybe absolute value here, right?
Maybe.
And that's what it is. If you look at these, it's let's write this down. The graph with the smallest A in absolute. Okay.
Wait, what in the first graph have the smallest A? Okay.
Okay. It would if I didn't add in the phrase absolute value. But I'm adding that phrase in. So the graph with the smallest A in absolute value is widest.
Oh.
And so it's not the third one. It would actually be the second one
Wait,
So-
absolute is the widest. Why do you put the widest?
is the widest because that's
White.
the widest. W-I-D-E-S-T.
Wait,
So
sorry. So if you didn't put in the widest, then it would be the third one. I can't say.
no, the first one would be the narrowest. So the graph with the smallest A in absolute value. Okay, there's an unwritten 1 in front of this one.
Is there that?
So the one with the smallest A in absolute value is actually the widest graph. So when you start seeing fractions in front of the x squared, that's going to be the widest graph. So this one is the widest, the second widest, third. And so as we go from wide to narrow, it's getting narrower as this number A gets bigger in absolute value. So which one's going to be the very widest
X to the 2.
Well, they all have x to the second power on them.
It's 1/4.
It's 1/4.
That's 1/4.
This one, yeah, the 1/4. What about down here? Which one will?
Oh, 1/3.
Oh,
1/3. Okay, so this will be the one. What's going to be next?
The
X squared. Just X.
Yeah, yep. And then the third one will be this. So that's how it works. So it gives you an idea of how it opens up. Now, so this one right here, it says graph the function. And if you go back to our first page, this was what we called the parent graph, y equals x squared. When you were studying transformations of geometric shapes, when you add a number to a function, what it does is it will move it up, or if you subtract the number, it will move it down. There's some other transformations we'll learn about later, but here it says make a table of values, but basically what I have is the parent graph that has been shifted up 3 units. Okay, for example, if I make a little table of values here, x, y, I'm going to just place 0 in the middle.
Exactly.
When I plug in 0 here and square it and then add 3, where do I land? 0 squared plus 3 is
0 squared plus 3 is 3.
3. So I have a vertex that's no longer at 0, it's now up at 0, 3. So if I were to describe the range of this, it's going to be y is greater than or equal to 3 this time, not 0. Okay, domain is still all reals. All fakes, yeah. All reals. We need to pick a value on each side of this, so it's your choice. You could pick, okay, -2 and 2.
Dare you.
So -2 squared, should have put it in parentheses, so you end up with a +4 plus 3 gives me 7. And so I have -2, 7 up here, and +2, 7 right here. And then we draw in our parabola. Now, when you have a 1 for your A, and you're just adding or subtracting a number from it, they'll all kind of look like that parent graph, but just be shifted up or down. So you could really graph these with just no table at all. At least for example, it says, how has the graph of y equals x squared minus 5 changed from the parent graph y equals x squared? Well, all that it's done is shifted down 5 units because of the negative. That's as a transformation. And so if you can kind of match it here, there's a very rough sketch, but I'm just drawing y equals x squared, but shifting it down 5 units. And that would change the range so that y has to be greater than or equal to
What?
-5. I'm going to kind of guide you through the classwork here. Let's see how you're doing on understanding it. So if you turn to the classwork,
Can I try this,
what's that?
I